Yo, Muso here. This is going to be more or less an AP level concept video on gravitation, and I'm going to connect this to circular motion. A lot of times we teach gravitation right around circular motion. That's what I do, and it causes students to think that means gravity comes from circular motion. That's not true at all. Circular motion has nothing to do with the force due to gravity. They go together, don't get me wrong, but an object spinning around won't have more gravity to it than an object that's not rotating or spinning around. Circular motion and gravity do go together, though, because we see things orbiting other objects in a circular path. And that's why they're connected, because of that, not because they actually cause each other's values to go up or down. So let's just think about this here. We've got our good old sun. I was looking for my orange marker. There it is. The sun, and not drawn to scale, the Earth, that pale blue dot, right? This Earth, somewhere off afar, and it is traveling in circular motion. We've already kind of talked about this. It's not actually a true circle, right? It's an ellipse, but I'm not going to get into that. We do know that the Earth has linear velocity, v. We know it's a certain distance, r away. We know there's got to be a force pulling inward in order for it to be in circular motion, right? Or else it would just go traveling straight forward. I've already covered all that. That force is weight or gravity between them, Fg. Okay? And so without tossing numbers in, just developing an equation, I want to look at my dynamics, Newton's second law, on the Earth. And I'm going to say the net force acting on the Earth is indeed centripetal, because it's going in a circular path. And therefore it is ma sub c. And remember, a sub c is really m v squared over r. So far, so good. But remember, anytime we set this up, we always have to identify what is that actual force. And in this case, that actual force is gravity. So F sub g. I'm going to rewrite this version right here. F sub g is m v squared over r. Well, we now know another equation for F sub g. The force acting on the Earth is going to be gm1 m2 over r squared. So I'm going to write that instead. So now I'm going to say it's big G, m of the sun, m of the Earth, over the r, s to Earth squared between them. This is also r, s to Earth. And now I'm going to subscript this more specifically as m sub e as the mass of the Earth, the mass of the object traveling in circular motion, which is the Earth. So I have g m1 m2 over r squared. See how I'm just putting subscripts here? It's the same original equation, equals this same thing, m Earth v squared over r. See what I've got so far? I'm getting somewhere with this, I promise. Now I'm going to take this m, I'm going to divide it over to cancel this m out. They're the same m. I should have kept a capital E here. I don't know why I did that. So let me use a different color so we can see me crossing these off a little bit more appropriately. I'll use red. So m is gone. This m is gone. I want to get v by itself, because this is giving me an equation I'm going to use to talk about its tangential speed. So I'm going to move this r over, and again, that r is s sub e. I don't know what's wrong with me and my subscripts. When I move my r up top here, r divided by r squared is going to cancel out one of these squared, cancel that up top. I'm going to rewrite this before I square root it. V squared is equal to big G, the mass of the sun, divided by the distance between the sun and the Earth. Now I'm going to square root it. This is an important equation. Now, I don't need you to memorize it whilst you're allowed to. There's nothing wrong with it. I needed to be able to get to it. I think deriving it is more important than memorizing it. And this is telling us the linear speed of any circular object, any planetary object, is going to be equal to square root of big G times the mass of the object it's orbiting divided by the distance between them. The speed of any object is equal to the square root of big G times the mass of the planetary body it's orbiting divided by the distance between them, or mass of the body it's orbiting. In this case, it's a star, right? Not a planet. That does mean, if we know how far away we are, and we know the mass of the thing that we're trying to orbit, we can determine how fast we need to be traveling so we can successfully orbit that thing. Right? Does that make sense? We know how fast we need to be orbiting to traveling that thing. And if we go faster than what we need, so if this speed goes up, and I talked about this in that other video, its orbital path will get further and further out, and it'll eventually go so fast it escapes the reach of the sun. That's that escape velocity term, so it can get out of our solar system. And if this speed goes down, then it's going to end up getting closer to our sun, and it'll probably eventually get swallowed up by the sun. That R value shrinks because they're inversely related. Interesting, right? I think it's kind of cool. But not only that, we can kick this up a notch. If you recall from one of the other videos I did, the velocity of any object in circular motion is really the circumference of that object divided by its period of rotation or revolution. So now I can replace this over here. I can say 2 pi r, and it's the distance between the sun and the earth, divided by the period, is equal to the square root of g ms over r s sub e. But now, since this is in the radical and this is out, I can probably do some fancy bit math here. I'm going to square both sides to get rid of that radical. Which means I need to square this, square this, square this, and square this. I need to square every single term. Oh, right? And now I can multiply that r over. And if I do that, then I'm going to get r cubed, aren't I? So I'm going to get 4 pi square r cubed divided by period square is equal to g m of the sun. And I'm just doing this so we can see here that we can figure out things like how far we are away from the sun are if we know the time it takes to make one revolution, 1 year, and we know the mass of the sun. Or vice versa, if we know how far away, we can determine the mass of the thing pulling us. This isn't really a new equation. This isn't a new equation. This isn't a new equation. They're all derived from the 2 already existing equations, just kind of combined together. And it's important to be able to do that. Okay? Okay, I think that's going to be pretty it. There's some more stuff involved. Actually, let me quickly kind of dive real quick into like satellites on our Earth. Let's say we want to put a satellite such that it has a specific period to it, like out here, and we want to know how far away does it need to be such that it goes around our Earth once every 24 hours. So now we know the period is 24 hours. We're looking for r. The speed we'll need to attain is this guy right here, right? And combine them together, maybe right here, solve for r, right? Solve for r. And we can say, okay, well, what's the period of a satellite? That's maybe 3 times the center of Earth. So we're 3 times away from the center of the Earth. We're way out here. What's the speed of that satellite? We can figure that out using this equation, as long as we know the mass of the Earth. Or what's the period of the satellite's rotation? We can figure that out using any of these. There's more to it. I'm not going to go and do it all for you. You need to do this part. Just understand that concept. Okay, I hope this helps. Thank you.